kx minus phi looks like. Now what I would like to do, I would like to draw a graph of this function which has a phase factor superimposed on top of this function so that you can make comparisons. When x equals 0, this function had a maximum. Okay? But in this function, when x equals 0, the function is a cosine of minus phi, which is not maximum. If phi is non-zero, this will give us a cosine phi, which is some number less than a. This function is going to be maximized whenever this argument equals 0. Right? That's the property of the cosine function. When the argument of a cosine function is 0, the function maximizes. Now, where does this function maximize? When kx equals phi, or when x equals phi over k. So this is some number, non-zero number, which means that this function is now shifted in position. It's the same overall form. It's again a cosine function, up, down, oscillatory, to and fro. But the 0 of this position has shifted. It has acquired a phase change. It's changed its phase. And the new picture would look like something like this perhaps. Now the maximum doesn't occur at x equals 0, rather it occurs at this point, which is phi over k. So now what we've done is, by adding a number to the argument of the cosine function, we have changed the phase of this wave. Which means that at x equals 0, the function is not maximized, rather it's some other value. So this actually, if this phi equals omega time, omega into t, if phi equals omega time, omega into time, then this pink function represents the function at some later time. Because phi equals omega times time, t. So the pink function represents phi, the wave drawn when phi is non-zero, which means the function at some later time. So this form, or this form, a cosine of kx minus omega t, actually represents a sine wave or a cosine wave that is moving with time, called a traveling wave, propagating wave. So this is a particle whose wave function is given by the one at the top. Its real part represents a particle that is moving in time. It's a traveling wave, a traveling particle. Likewise, the imaginary part, which I've drawn over here, is also going to move forward in time. So now on one graph, I have drawn the wave function at 2 times. The yellow picture is a snapshot at one time, and the blue picture is a snapshot at some later time. Right? So this is what this wave function means. And if I were to look at the properties of this wave, so here I'm plotting the real part of the wave function. This is x. So I'm plotting with respect to position. At one point in time, frozen in time, I have taken a frozen picture, frozen in time, at one snapshot, at one instance. And this is what the wave function looks like in space. Because this is the space axis, x. This is what it looks, this is what the profile of the wave function is along the position axis. And from basic school level physics, you know that this is the wavelength, lambda. You work in the math, this turns out to be equals to 2 pi over k. This k is the same number that we put in here. This is called the wavelength. K is the inverse wavelength, also called the wave number. And from de Broglie, the French physicist, you know that this k is actually related to the momentum of the particle. So, a particle P H bar k. This is the de Broglie relationship. Remember? So now the physics is coming in. It's sorry? G. Okay. I'll answer that question in a minute. Okay? टाइम आप ले आए हो बीच में, मैं अभी उसका जवाब दूंगा, मैंने देना था जवाब. So I can choose any phase, I can put any number here. Here I am defining this to be the wave function. So I have an omega t, so my phi is omega t here. Right? Sorry? ये वैसे पढ़ी हुई थी Broglie की equation? Okay. So what you studied in this course probably is momentum of a particle is h over lambda. This is what you studied. Okay. So but I've defined lambda to be 2 pi over k. So you work out this relationship. So why is this 2 pi over k? This you can work out yourself. So if this is a cosine kx. Cosine is a periodic function. So you can find out the period in space. That turns out to be 2 pi over k. Okay, this is quite easy. Do it as a homework. No problem about it. But this is the de Broglie relationship you've already studied. What this tells us is that if you have a particle of momentum p, mass times velocity, then we know that there's a wave associated with the particle because of wave-particle duality. Now that wave may have a wavelength, and the momentum, which looks like a particulate property, because if this is a particle, if it hits me, I feel the momentum, I feel the pinch. It has momentum. This moving particle has momentum, so it looks like a particulate property. And this wavelength looks like a wave property. And this is a strange equation. It's simple, innocuously simple, really simple, but it's strange because it connects a particle property with a wave property. And this is the de Broglie relationship. Now, if I use this recipe over here, I can switch from lambda to k. So I can write this as h 2 pi k. So h over 2 pi occurs so frequently in physics, it's given a special name, h bar k. Okay? In America you would call this h cut. In English colonies you would call it h bar. So this is h bar k. Now this wave that I've drawn it with respect to x. The period in space is called the wavelength. Right? That's how we define the wavelength. But what I could have done, I could have chosen, I could have chosen to draw the wave function not in space, but I would have looked at one point in space, just one point in space, and I would like to see how does the wave change with time at that point in space. So I have 2 points of view, 2 perspectives. These are pictures frozen in time over space. I could have drawn a picture frozen in position, which means at one spatial location, but how does the wave change with time at that position? Just imagine you're sitting on a seat, you're in a boat, it's a calm afternoon and the sun is shining bright and it's very calm and you're just reading a book, but you're on a boat, on a small boat, and the sea is calm. You stay wherever you are. There's no wind, so the boat remains static. But occasionally the boat bobs up and down. So a wave is propagating. You're not changing your position, but you're experiencing to and fro motion with time. So I could also draw pictures of the wave functions with respect to time. Time. Okay? I can fix x. I can fix x. So I can choose one location, x, and see how the wave function changes with time. It's the same wave function. A cosine kx minus omega t. So I'm plotting the real part of the wave function. A cosine of kx minus omega t. So I choose some x. In order to draw this, let's choose some x. Let's choose x equals 0. Okay? Now the point is that each of these terms just changes the phase. Nothing else. So I choose x equals 0, I get a cosine of minus omega t. Cosine is an even function, so I get a cosine omega t. Now what does the plot look like? Just a cosine again. Just like this. अब negative t में क्यों जा रहा है? Right? Because we can choose any, there is no such thing as zero time. You can choose any time to be zero time. It's just a fiduciary reference. So this is how, at one point in space, the wave function changes with time. And just analogous to what I've written over there. This is 2 pi over omega. If I were to draw the wave function with respect to x, this is 2 pi over k. Analogously, बोलोगे जा रहे हैं आप? चलेंगे. Let me finish. So analogously, analogous to that, what I've written over there, this interval is 2 pi over omega. देखो यहाँ kx था जब, when we had kx here, the period was 2 pi over k. Now when we plot with respect to time, the period is 2 pi over omega. This is called the time period. So omega is a frequency in time. K is a frequency in space. Omega has units of 1 over second. K has units 1 over meters. Position and time go hand in hand. Okay? Yes, there was a question. Yes. मैंने x को 0 रख दिया. So I am drawing this waveform at one point in time. And just coming to you, if I were to plot the imaginary part of this wave function with respect to time, so the imaginary part is a sine of, this is 0, at the same location, sine of minus omega t. Now this is minus a sine omega t. Minus a times sine omega t. Now if I were to plot this, this is what I would achieve, right? So now we've drawn the wave. This is the simplest wave function besides a constant wave function. The simplest wave function of a hypothetical particle. Why hypothetical? I'll explain in a minute. That can be drawn on a blackboard. Yes?
Sir, there is no upper limit to the time reference, right?
Oh, that's why it's a hypothetical particle.
Sir, but if there is no upper limit to the time, then when we take psi square, which is equal to the probability, then if time goes up till infinity, the probability that is confined to 1, then
It breaks down.
yes,
That's why it's a hypothetical particle. So this, now let's come to the physics. This wave function that I've written for a beginner is the easiest wave function you can think of. It represents a wave that exists at all points in space because it goes from minus infinity to plus infinity. So it's a ubiquitous particle, just one particle that exists everywhere in space. So it's hypothetical. Likewise, it exists at all points in time. Let me finish, please. It exists from eternity, negative eternity, from Big Bang, because that's the limit, to, say, if you believe the Day of Judgment, or the Big Crunch, whatever you would like to say, but it exists from never to ever. This is a hypothetical particle. It's also called a plane wave. But it's a nice construct because it's easier to understand, and any other wave function can be decomposed in terms of these plane waves. That's called the Fourier series. You might have come across this, Fourier transforms. But any wave function, so this is an example of a wave function, a real wave function of a particle. Of a real particle. You can have many wave functions of this kind, add them up, and synchronize their k values, and add them up in such a way that you get this one. Real wave function of a real particle. So that's why it's important to understand these plane waves. Now I'm going to come to the uncertainty principle, but there were a few questions. Yes? No, but even quantum fields cannot, so the argument, so if I have psi, psi is just half of reality, because psi alone doesn't tell you much. If you would like to interpret this, what you would like to do is you take the modulus square of this. If I have a particle with a wave function that I've written at the top left corner of the blackboard, and if I took that wave function and took the modulus square of this wave function, which means I'm taking the complex conjugate of psi and multiplying it with psi itself, what would the answer be? But for that wave function, what's the answer? नहीं कोई आंसर बताओ ना. A square. If A is real, I'm assuming A is real, so this is just A square. Does this depend upon position? Constant. Does this depend upon time? No. Alright, so let's make a graph of this probability density. Right? This is how you interpret wave function. You take the modulus square. Let me finish an argument. You take the modulus square, that gives you the probability density. What's the probability of locating a particle at a certain point in space? That's what psi modulus square is. X, 0. So if I would like to make a graph of this A modulus square, now A can't be 0. Because if A is 0, the wave function doesn't exist, the particle doesn't exist, you're talking about vacuum. So in order to make meaningful discussion, you have to have A non-zero. So if I would like to plot A square with respect to X, it doesn't depend upon X, what would the graph look like? Straight line from minus infinity to plus infinity. Now the area under this graph must equal 1, because that's what probability means. But now you have something which is non-zero, a baseline. The area under this graph can't be equal to 1. It's infinity, because it's non-zero. This doesn't make sense. That's why, hopefully I've answered your question. That's why it's a hypothetical particle. ये यहाँ तक समझ आती है? Now if I would like to make a graph of this, it's a straight line. Now the area under this graph is the total probability of locating the particle somewhere in space, anywhere in space. That has to be 1. So the area under this graph has to be equal to 1. But it can't be equal to 1 because this is extending from minus infinity to plus infinity. The area under this graph is infinity. So that's why this is a hypothetical. No particle can have that wave function, but this is how you do all of quantum mechanics in modern physics because it's easier to understand. And all other real wave functions like this wave function, which is called a wave packet, is actually composed of many plane waves of the right amplitude and the right wave number added together in a mathematical synchronization process which is called the Fourier transform, Fourier series, Fourier decomposition. ये लफ्ज़ देखा है इस कोर्स में? इसलिए मैं भी नहीं बता रहा। हैं ये वेव पैकेट क्यों है? खड़े खड़े हो जाओ, उनकी तरफ मुंह करो, सवाल पूछो।
अभी कोई पार्टिकल है जो मुझे बना रहा है, ठीक है?
जो आपको बना रहा है।
I am composed of carbon atom, very stable carbon atom. You can confine its space from one point to the second point, boundary conditions are, and you can confine the start of its time, but you can't confine the end of its time. It will go on and on and on. Time has no limit. So how can that have a wave function associated with it?
No, but every particle has to dissipate. In reality, if I have a laser produces light photons that have a wave function that are approximately a plane wave. When you study optics, आपने telescope, microscope, you also study plane wave fronts. Those are plane waves, but those are approximations. They don't occur at the edges of your instrument. So if I have a laser that's shining light, that light has to deflect from some boundary. So the light is spatially confined. Light is going to dissipate with time as well. So it's not going to extend up till infinite time.
But it dissipates, but it won't destroy itself.
What will not destroy itself?
The light, because it is something.
It's going to lose all its energy until the energy goes to zero. Into some other forms of energy, irrecoverable forms of energy. Alright, so let's move on. I would now like to connect this with the uncertainty principle because this is something you've already seen. Agree? Now this gentleman, Mr. Ahmed, asked this question, how do you construct this wave packet? So now if I were to take, let me give you a simple motivation for this. I will not go into the math because that's, Dr. Faryad is not going to like me if I do lots of math. Maybe he will, but I won't do lots of math now. So if I have a graph, a wave, and then I have another wave in the same, so this is space axis, this is x. Now what I would like to do, I would like to draw, in the same region of space, let's draw another wave. That wave I'm going to draw as a dashed line. Okay? Now in this region of space there are two waves. Both of these waves have the same amplitude but they're shifted in phase by 180 degrees. One is a sine wave, the other is a cosine. They exist in the same region of space. Now these waves can superimpose. And when they superimpose, since they're totally out of phase, the resultant wave in this region of space is just zero. Now by having two waves which are destructively interfering, I'm constructing a new wave which is non-existent. Likewise, I can have a wave, say a cosine of k1x a1. I draw this wave. And then I draw another wave, A2, some other amplitude, cosine of K2x. Some other wave number, some other wavelength, because wave number and wavelength are inversely related. Some other wave, say, suppose A2 is larger and K2 is smaller, which means wavelength is longer. This is a picture of this wave. And then I have another A3 cosine or some other K, K3x. And now suppose A3 is really small and K3 is really large, the wavelength is short. Now I have a large number of waves, large number of them, of different amplitudes, different Ks, and I add them up. Plus, plus. I will construct a new wave. Right? That wave will have a new shape. It could have a shape like this, called a wave packet. Now this looks like black magic. Oh, how do we know what A's to choose, what K's to choose? But actually this is not black magic. There is a process of finding out these A's and these K's. That process is called Fourier transformation. This is a process. For example, just let me write down the formula. I'm not going to explain it. If you don't understand it, no worries. An equals. So this is going to have a certain functional form, fx, right? Some form. An equals fx cosine of n kx summed over. So let me do a dx summed over a. This will give me the value of a at some k. So you don't need to understand, but there is a proper procedure of finding out these Fourier coefficients and these wave numbers. What case do we choose? All right, yes. आएगा हाँ यानी आपने देखिए वेव फंक्शंस आपके पास ऐसी सिचुएशन भी लेट मी गिव यू एन एग्जांपल अब नाउ यू आर आस्किंग क्वेश्चंस व्हिच विल लीड मी एस्ट्रे बट लेट मी गिव यू एन एग्जांपल Well, I'll do it really quickly. So if I would like to make this function, psi x, like to make this function. Now this function looks like a real function because it's confined only within a certain region of space and it's zero elsewhere. Now what k's should I choose? And how much of each k should I choose? So if I look at this wave function, I need to choose the following. I need to choose all of the possible k's, but the higher k's have a vanishingly small amplitude. Okay? So all k's, but the higher k's with a vanishingly small amplitude. No k should be chosen of this value. In fact, if this is a, then this is, I think, pi over a or 2 pi over a. I will not have any k of magnitude pi over a, and so on. So I will choose all possible k's, but the higher k's will have exceedingly small amplitudes. And if I truncate this, I can't choose high k's, then this function is going to smoothen out a little bit. So these are mathematical details which are not really, I don't want to delve into them. Zero पे आप कह लें कभी नहीं जाएगा, but it becomes smaller than our experimental uncertainty. You can't detect it. Vanishingly small. ये periodic function नहीं है. नहीं करेगा. अगर आप ये वाले wave functions, ये वाली k values लें, तो आपके पास ये एक periodic function आता है. ये कभी भी रिपीट नहीं होगा. ठीक है? इसको आप अगर आपने फाइंड करना है a k, this is a, so this equals this function psi x cosine of kx dx, where x goes from minus a to plus a. Solve this, you will get this form. Okay? आप ना समझे कोई बात नहीं, क्योंकि अगर मैंने ये समझाना शुरू कर दिया तो I lose out on 99% of the class. इसका फोरियर ट्रांसफॉर्म sin x over x ही है. All right. Any more questions not related to the math? Because if I go into the math, I'll have to forego other important discussions.
Yes, sir.
All right, so now let's talk about the uncertainty principle. And how does this relate to the uncertainty principle? Suppose I have a plane wave. The plane wave, if I were to draw the plane wave, once again it's hypothetical. Question. If an electron is my pet elementary particle, and I ask you the question, an electron has that wave function, the one that I've written at the top left of the blackboard. अगर आपने फोन इस्तेमाल करना है, बाहर चले जाएं, excuse me, we're here for a purpose. If an electron, my pet elementary particle, has that particular wave function that I've written at the top, and I ask you the question, where is the electron? Anyone else? I would like to look at some other people. Yes.
We cannot define this exact location. We can say that it is more probable to be in this area.
Right. So for this particular wave function, the probability density is uniform everywhere. So it's likely to, if I were to do an experiment and locate the particle somewhere, it can pop up anywhere in space with equal likelihood. Okay? So so we can't definitely answer the question, where is the electron? In fact, in quantum mechanics, this is a meaningless question. What we could do is we perform an experiment and the electron pops up somewhere. Okay? So if this particle has this particular wave function, we are totally uncertain about its position. Right? So we are uncertain about its position. Yes. Because the probability density is uniform everywhere, it's same everywhere. Remember, it's a hypothetical particle, but it can be everywhere. You have experiments where the electron can exist in an atom. What are wave functions? S orbital goes up and down somewhere. The S orbital is not somewhere, it's everywhere. P orbital is everywhere. Yeah, इस तरह हाथ कर दे. जी. बिल्कुल hypothetical ही है बस. Hypothetical particle, बिल्कुल सही. नहीं हो सकता. Alright, so we are uncertain about its position. Now, what does uncertainty mean? Uncertainty means there are different ways of defining uncertainty. Now, when Werner Heisenberg defined uncertainty, he used the wrong word probably. Because another way, a proper way, or a more illuminating way of defining uncertainty is that it's the range of possibilities. So I can define uncertain. Big uncertainty means a big realm or range of probabilities. If the position is uncertain by a large amount, it means that if I were to measure the position of such a particle, then the particle's position, the outcome of the position, can pop up in a long, large range. This is a long range realm of possibilities to find out the particle somewhere in space upon measurement. So the position uncertainty is large for a plane wave. It's really, really large. However, if you look at the momentum of this particle, this wave, this hypothetical wave, has a fixed period in space. It has a fixed k. It's not changing. This wave is not. It's fixed. This is a precise k, a precise wavelength. It's a totally periodic function, smooth function. So even though the realm of possibilities of position, which we denote by delta x, is humongous, it's so large, we're definite about its momentum. Because p and the wavelength or wave number are related. There's a precise k. Okay? So, if delta x is large, delta p is 0. There's no uncertainty in the momentum. We precisely know what the momentum is. If somehow we were to spy upon the wave function and we did some masterful experiment in which we could find out the wave function, and if this turned out to be the wave function, then we would know its momentum. But we would know nothing about its position, because a measurement of the position will yield one outcome, just one outcome, but out of a large sample. But the position, the momentum measurement will yield a precise value. Okay? Excuse me? G. देखो यार, this is k fixed. Is this changing with position? With time? At some other point in time, the wave function just shifts, it's a traveling wave, but k is not changing. Lambda is not changing, that's why p is not changing. So it's one precise value of momentum, yes. नहीं, मैं बताता हूँ नहीं, बिल्कुल नहीं. Let me draw a diagram to explain this. Now this kind of diagram is called let's call this an uncertainty diagram. Now you will not find it in many textbooks, but it's easier to understand the uncertainty principle using these diagrams. So this is the position axis and this is the momentum axis. If my wave function, which now I would like to write again, is at some point in time, so I don't need to write time over and over again, is AEI kx minus omega t. At some point in time, that's t naught. I can choose my time to be 0. So for this particular wave function, we know that delta x is really large. Right? We plotted the wave function. So the realm of possibilities before measurement is really large. The uncertainty in this x is really large. There we are. But the uncertainty in momentum is 0. Right? So how will you draw this on the blackboard? Yeah, just see, I would like to draw some locus, some region on this blackboard which has x really large with one, but just one value of p. I would like to draw a locus or a region of points. Anyone? Because, so this is a diagram. I would like to draw the uncertainties for this state. Momentum certain hai? Certain hai na momentum, it's precise k. But if you drew the wave function in position space, it extends all over in space. कोई भी चलो हाँ. Exactly. So this is the uncertainty diagram for this state. It has one precise value of p, say p naught, some value of p naught, which is equal to h bar of this k. Let's call it k naught, some value of k naught, right? But the x has an infinite realm of possibilities. This actually line tells us that delta x is infinity. But you precisely you can precisely predict, write down, prescribe what the momentum of this particle is. Yes?
Is this for an ideal case? Reality mein to ye aata hoga.
This is ideal. You cannot have a sharp momentum. This is ideal. But it's important to understand this. Okay, now let's suppose that I do measure the position of the particle. I have an electron microscope or some microscope which exists with an omnipotent beam which can look at everywhere in space. And you perform an experiment, you decide, okay, one morning you decide you would like to find out where the electron is. And you haven't learned quantum mechanics. So you perform an experiment, you take an image, you have a camera of really wide field of view and you image the electron, single electron, just one electron. And it turns out to be somewhere on the x-axis. Right? That's what the outcome of an experiment. The experiment can't really show you the particle is this everywhere. Because when you perform an experiment, you're actually doing a measurement. And when you do a measurement, the wave function collapses. This is a word because that's how experiments work. The wave function collapses. You see the particle somewhere. It must pop up at some precise location in space. Let's call that location x naught. Okay? Now, at the instance you do a measurement, now this is an axiom of quantum mechanics. This is axiomatic. Axiomatic means this is how nature works. This is how quantum mechanics works. How nature works in quantum mechanics describes nature, has the ability to describe nature. You have this particle whose wave function is ubiquitous, it's everywhere. The wave function is everywhere. Now you look at the particle somewhere, and it turns out it says, hello, hi, I'm at x equals 3 centimeters. I'm at x equals -9 angstroms. That's where I am. So now you have created, you've done a measurement. The wave function is no longer what it used to be. Previously the wave function was that this ubiquitous wave function which was everywhere. But now it's no longer the case. Now you've seen with your own naked eyes that the electron is at -9 angstroms. Some value of x, which is x naught, it has popped up, waves up, and oh, I'm here. So now the wave function can't be this one. The new wave function is created. That's the key. When you do a measurement, the wave function, the original wave function collapses, it crumbles. It crumbles out of order, and in the process you create or generate a new wave function. Okay? So the process of measurement is creating a new wave function for the same particle. Okay? And that's why you say that the quantum mechanics is strange, because when you create a wave function, when you do a measurement, you are creating a new wave function. You're saying you're creating a new state. Another name for the wave function is the state. Previously, the particle existed in this state. The uncertainty diagram looks like this. Now you have pinpointed the location of the particle. It could have come up at any x because the probability distribution is uniform. But once you actually do a measurement, it just realizes or actualizes or materializes at one particular x. Even though realm, that's why this word, I really like this word realm. Mumkinat ki duniya. Mumkin hai, bahut सी चीजें mumkin hai. Many things are possible. The entire range is possible. But only one outcome is actualized. One outcome is materialized. That particular outcome could be some x. Let's say it's x naught. Now a new state has been created, a new wave function has been created. If I were to draw the wave function after the measurement, just after the measurement, this wave function is no longer going to be a plane wave. Rather, it's only going to exist at x naught, just x naught. And it's going to be just a spike over here, just at x naught. In mathematics, this is called a Dirac delta function. You don't need to understand this, but it's denoted by delta. Delta. It's a function of x, right? It's a non-analytical function. It's a strange kind of function, minus x naught. So this function exists only when the argument is equal to 0. This function exists. The property of this function is that it's denoted by delta. Every function has some argument. When the argument is 0, the function exists and it's 0 elsewhere. So this function is non-zero only when the argument is 0, which means when x equals x naught. This is called the Dirac delta function or the Kronecker delta. So after measurement, you have created a new state. And this is what the new wave function looks like. Now I would like to complete the story, then I'll take a question from you. This new wave function, the uncertainty in the position of this new state is now 0. By virtue of the uncertainty principle, the uncertainty in the momentum must now go to infinity. Which means that if I were to draw a picture of the wave function in which this axis were the momentum axis. Now I'm drawing a wave function with respect to momentum. There's nothing special about x. I can draw with respect to momentum as well. So for this particular wave function, the blue one, after the measurement, there are all possible values of p are possible. So the uncertainty in momentum becomes really large. Hence, if I would like to draw this new state on this diagram, now it's going to be a vertical line at x naught, and the momentum becomes totally uncertain. So now this was an uncertainty line. Now you perform a measurement on the position. The line on the uncertainty line changes by 90 degrees. Yes? Question?
My question was, this is the wave function at that instant when we have situated on that rotation. But if we were to determine its location after 1 second of this instant, it would be C, the magnitude of C in all directions.
Now that depends upon, so you've done a measurement, that depends upon what environment the particle is in. If it's a nice clean environment which is space, vacuum, it's going to stay there. Okay? But generally that's not the case. Every particle changes with time. And this is what another equation of quantum. So Newton's laws of motion tell you how objects change with time when you apply a force on them. There's an analogous equation in quantum mechanics that tells you how the wave functions change with time. That's called the Schrödinger equation. And probably you learn about this in this course. Yes?
You were said that the uncertainty in momentum is like 0 in the first case.
Yes.
Sir, आपने बताया कि एक infinite है. लेकिन सर अब आपके लिए particle हमने pinpoint कर दी है. दूसरा momentum the uncertainty momentum is infinite. How is it? तो भाई साहब एक ही टाइम से बता रहे हैं कि same रहेगा तो momentum आपका same रहेगा.
यानी इसकी जो केस है वो infinite केस है. इसको कंपोज करने के लिए if you would like to make, you see, I'll answer your question. Look at these graphs. Okay, last point, please be patient. Just 3-4 minutes. This is a wave function that exists in just a small region of space. Okay? That region of space is just from minus a to plus a. Okay? This is called a localized particle, a localized wave function. It's at a certain location only, it's confined to that location. Now, if you look at the possible momentums or k's, this is the same wave function in momentum space. Now, you would like to tell what kind of k's, momentums would you like to add up in order to construct this? In other words, what's the momentum of this particle? It has all these possible momentums. It has none of pi over a, none of 2 pi over a. It has maximum momentum of 0, some momentum between 0 and pi over a, and so on. So it has all of these momentums. Answer to pura dene do. Now if I would like to compress this wave function in space, I squeeze it in space, which means I am decreasing delta x. I am decreasing the uncertainty in position. I'm squeezing it in space. What I'm actually doing, if I would like to find out what momentums does this squeezed wave function contain, it contains a wider range of momentum. So this wave function in momentum space fans out. अगर आप, let me give you an example. अगर आप straws लें, अगर आप उनको गुच्छे में हाथ में पकड़ेंगे, ठीक है? तो अगर आप tightly उनको पकड़ेंगे, उनको localize करेंगे space में, तो they will start pointing in many different directions. Which means that the velocity vectors are pointing in different directions. They can point in different directions. They can go off in different directions. अगर हम हल्का पकड़ेंगे, delocalize कर देंगे, so they will all be straight. So there is a seesaw relationship between position and momentum. If you squeeze something in space, it's going to expand its momentums. It's going to go up in momentum. Just look at the plane wave. One momentum, but all positions. If I squeeze this in space to such an extent that it actually becomes just one small rectangle, some really small squeezed rectangle of 0 width, I will get all possible. This will turn out to be a uniform function. All possible momentums will exist, and I will get the same result that I've drawn over there. Alright, I'll just take 2 questions before we end the class. Someone new? Yes, up there. बाद में जवाब दे दूंगा, कोई नहीं. You can't do it. This argument doesn't work in quantum mechanics. You divide by time, then you multiply by mass. It's not going to work that way. It doesn't work like that. Yes, there was one question. Have patience to listen to questions. Yes. First question is, okay, if the momentum changes, where does the energy go? When you do a measurement, the energy of a particle goes into some other form. For example, you have a single photon, you're detecting the photon. The wave function collapses, all of the energy of the photon now goes into the electronic pulse that is created by the detector. So the energy is conserved, but it goes to some other form. Second question, real and imaginary? Well, the real and imaginary are just two parts of the wave function. Real is not real and imaginary is not, real is not more real than the imaginary. These are just words. These are two components of the wave function. The key about quantum mechanics is that you're always dealing with these complex numbers. There is always an iota, and this is where quantum mechanics is different from classical mechanics. But the real is not more real than the imaginary. These are just misnomers. These are two components of the wave function. Okay, we'll finish the class and I can answer questions afterwards, after the class.